Hi, welcome to Mat154 Pre-Calculus College Algebra through Eastern Arizona College. And we're going to discuss rational numbers as exponents. So we're going to review some of the laws of exponents and things. But these are basically the ideas we're going to do. We're going to write expressions with or without rational exponents. So we've already learned how to write them as a radical, but we're going to learn some new things. Write expressions without negative exponents. You can change negative exponents to positive. We're going to use the law of exponents with rational exponents, and we're going to use rational exponents to simplify radical expressions. So we've got a lot to do. We got our work cut out for us. So let's see what they're talking about first. Let's take a simple example. Suppose we wanted to find the, the cube root of x. X could stand for a number, or it could stand for anything. We can also remember this is called the radical, this is the radicand, and this is your index. But it also has a power, and the power here is 1. Anything without a power is always 1, to the 1 power. So we can write this also as what we call, instead of radical form, we can write this in what we call rational form. In rational form means that we're going to write the x. This is our radicand, and we're going to put power over index. Power divided by index, or power over index. And now we have changed this radical to look like this. Well, let's suppose we had the square root of x, just the square root of x. Well, again, this has a power, which you can't see. The invisible power, let me get a different pen here. The invisible power of 1. And it has an index, which you can't see, which is a 2. So we could still write this, even if it's just a square root, we can write it as x to the 1/2 power. Okay, let's suppose we had the cube root of 4, let's make it 4 squared. Okay, so we could write that as 4 power divided by index, 4 to the 2/3 power, if we wanted to. Okay, suppose we had the cube root of 27. Okay, we could write this as 27 to the 1/3 power. Usually it's easier to work in radical form because it's easier for us to visualize it than it is in rational form. So we could switch back. If it was in rational form, we would go into radical form, and then we could write this as the cube root of 27, which is the cube root of 3 cubed, which is just 3. So our root number, the cube root of 27, is 3. All right, so let's try another one here. Let's take one out of the book. They had x to the 1/2 power. Let's write that in radical form. That would be the square root, x. Power is 1. No need to write it down. Index is 2. Power, index. And I always think of pi, pi, even though it doesn't make 3.14. I think of it as pi, and you can kind of remember it's in that order, power over index. Okay, here's another one. ABC to the 1/3 power. Okay, so that means the whole quantity is under the radical. And you probably want to keep this parentheses. The index is 1. You can write it or not write it. I mean, not the index. The power is 1, excuse me. The index is the bottom number. That's 3. And that goes in that little slot right there. So we can write things in rational form or different form. Let's try a few more. The fifth root of 7xy. Let's translate that to rational form. 7xy, power is 1, index is 5. Just like that. You could also write each one of these individually, but it takes more time. Okay, here's another one. 8 cube root of xy. 8 is outside, so it's still going to stay in 8. xy is inside. Power, 1, index, 3. 8xy to the 1/3. Okay, you just don't want to write the 8 with the xy because only the x and y are raised to the 1/3 power. The 8 is separate. Okay, and the last one, we'll try this one. A little bit more complicated. X cubed y over 9, the 7th root. So you can take roots, any kind of root. Okay, so again, we're going to pull this out. X cubed y, put it in the parentheses. The power of this whole thing is 1. The index is 7. So we can go from radical to rational, rational to radical. We can switch back and forth. So the general rule is this. I'm just going to jot it here. A to the m over n would mean radical A, power m, index n. Or vice versa. Power, index. Power, index. Another interesting thing is, let's take a look at this problem. 27 to the 2/3 power. We can do this two different ways. We can write this as the cube root of 27 squared. The problem with this, let me move this out of the way. The problem with this is that when you have this, you're going to have to square the 27. So you need a calculator probably, or, you could do it without a calculator, but it saves a little bit of time. So you got 27 squared, which is 729. And now you got to take this cube root of 729. So we're going to go up here second. First, we're going to put in the index 3, second up arrow, 729 equals 9. Well, that's a little time consuming. First, we had to square this and we had to take the cube root of that. Another way we can handle this problem is we could write this as 27 cube root, but then we could put the power on the outside. The power can either go inside or outside. On this problem, we're taking the cube root of 27. The cube root of 27 is 3. A little bit easier to do. We might remember that. And then we're going to raise it to the second power, which is 9. It takes the same amount of steps, but these steps are a little bit easier because we're working with a smaller number. So usually we put the index on the outside. Let me write that a little bit neater. We write the 27 like this, and then we just put the 2. You can put a whole parentheses around this, or you can just kind of jot the 2 like that. See? And again, that means the cube root of 27, 3. 3 times 3 times 3 is 27, squared, 9. Okay, let's try another one. 4 to the 3/2 power. So again, I'm going to write this as the square root. First, I'm going to put my 4 underneath here. power is going to be 3. I'm going to put the power on the outside, and the index is a 2, which I don't need to write down. So this is really square root of 4, which is 2 cubed, which is 8. You could write down to 2. I mean, it's not totally wrong. It's just that we, by convention, don't usually write down to 2. So that's simply saying we have 4. Instead of taking 4 cubing it, 64, and then taking the square root. You could do it that way too. I mean, it's not wrong to do it this way. And then you would just cube it, which is 64, and then take the square root of 64, which is 8. But you're working with larger numbers, so you always try to keep it as small as possible. So that's kind of an example of those things. There's a couple more examples. Here's the cube root of 9 to the 4th. So again, on this particular problem, cube root of 9 to the 4th, we're just going to write this because this is not going to come out an exact answer. Let's write this without the radical sign. Let's put it in rational form. This is going to be 9 power 4 index 3. And I guess I should have put the 3 a little bit closer in there, but so we would probably just leave the answer that way, 9 to the 4/3. It can be improper. We usually don't change this to 1 1/3. You just leave it improper. Here's another one. The 4th root of 7xy all to the 5th power. Okay, so we have 7xy under the radical. Power 5, index 4. Now it's in rational form. So you want to practice those. Okay, another thing that we can have is we might run into something like this. Suppose I had, so let me do an easy one. Suppose I had 4 to the negative 1/2 power. Well, the first thing we want to do is if we have a negative exponent, we want to change it to a positive exponent. It's like an elevator, it's going up and down. We're going to move the base down on the elevator, going down to ground floor, and now my exponent becomes a 1/2, a positive. And we're going to put a 1 over that to hold the position. So it's really the fraction 1/4, but only the 4 is to the 1/2 power. So this would be, let's put it in radical form, this would be 1 over the square root of 4, power is 1, don't need to write it, index is 2, don't need to write it, and so it's 1 over the square root of 4, which would be 1/2. So 4 to the negative 1/2 is 1/2. So it's just another way of writing it. Let's try this one. 9 to the negative 1/2. That would be 1 over 9 to the positive 1/2, which is 1 over the square root. So you want to kind of recognize a half as being a square root. A half, a third is a cube root. A fourth is a 4th root. So if it's to the 1/2 power, you just recognize it. Oh, that's the square root of 9 power index, which is 1 over 3. See? So if you can recognize 1/2 powers are square roots, 1/3 powers are cube roots. Okay, but here's one that's a little harder. Suppose we had 5xy. And I'm just using examples. This is around page 378 if you have a book. Negative 4/5. Okay, let's rewrite it. Move that back down. 4/5 power. The power becomes positive. Maybe they just want us to leave it in this form. They don't want it in radical form. If they want it in radical form, then it would be 1 over radical sign 5xy. I'd keep that in a parentheses. And since we can't really do much with that, I'm going to put my power and then my index. I could put the power inside or outside. On this one, since we're not going to simplify it anymore, I'd probably just put it inside. So now we can put it in rational form or radical form. All right, here's another one that's interesting. 64 to the negative 2/3. Okay. Well, first of all, it's 1 over 64 to the 2/3. Power. Kind of sloppy there. Put it in radical form. 64. Let's put the power on the outside. The power is 2, and the index is 3. Okay, can I find the cube root of 64? Because sometimes we see 64, we think it's always a perfect square. So let's go to our calculator, hit the index is 3. Second up arrow, 64. And I'm going to finish the parentheses, equals, and I've got a syntax here. What did I do? Cube root of, oh, I didn't have a parentheses there, so I added one where there shouldn't have been one. Let's go back and clear that out. Okay, there we go. Equals 4. Okay, so the cube root of 64 is 4, but we still have the square. So that's 1 over 4 squared is 1 over 16. So all I did here was take the cube root of 64, but I still had this power of 2. So the cube root of 64 is 4. All right, let's try another one. Here's a mess. Grab another sheet of paper here. 4x to the negative 2/3, y to the 1/5. Whoa. Well, we could write this in radical form. We're just keeping it in rational form. This would be 4. The x to the negative 2/3 is going to go down. But the y to the 1/5 is positive, so we're going to keep that on top. Okay, so it's like an elevator. The parts that are negative, we can send down if they have a negative exponent, not a negative sign in front, but a negative exponent, that can be sent down. And then the rest. Let's suppose this was a negative 4. It would still stay a negative 4. We would not send a 4 down. Only the part that has a negative exponent. It can go down or it could come up. Let's see if they have one like that. They don't. Okay. Let's try this next one. We have 3r over 7s to the negative 5/2. Well, one thing we could do is we can make this positive on a fraction by simply flipping the fraction. 7s, 3r, make it a capital R, and then we can just change the sign to positive 5/2. That's probably the fastest way to do it. If we had to put this in radical form, maybe they just asked us to leave it in this form and ask for it. But if we wanted to put it in radical form, then we would write it as 7s, 3r. But let's put that in parentheses, power, 5, index, 2, so we don't have to write it. But you want to put a parentheses here. You probably would not carry this out. You'd probably just either leave it in this form or this form, depending on what they're asking for. Okay, quick review of how we deal with laws of exponent. So I'm gonna show you with some just typical examples. Suppose we had 2 to the 3rd times 2 to the 5th. If the bases are the same, we keep the common base. It could be a 2, an x, a y. Both the bases are the same, and we add the exponents. 3 plus 5 is 8. So this would be 2 to the 8th. The bases are the same, we add the exponents. Okay, for multiplication. For division, here I use x's. If the bases, again, are the same, this has to be an x, this has to be an x, then we simply subtract exponents, x to the third. If we have a power raised to a power, this is the only time we ever multiply exponents. It's kind of like distributing. So we're going to distribute, we're going to multiply, and this would be a to the 6. Power to power, you're going to multiply. I guess I should write. This was subtraction. 3 times 2, a to the 6. That's the only time. Most of the time, we're going to add or subtract. If we have multiple things in here, and I'm just going to use an m. Let's make this an n. This would be a to the m. See, we're going to multiply the exponents, and here we're going to multiply n times m. So we're going to multiply exponents. We're going to multiply everything that's in here. So let me give you another example. Say we had 2x squared y to the third. Then this would be 2 to the third, x to the 6, y to the 1 times 3 is 3. If you wanted to at this point, then you could simplify 2 to the third is 8, x6, y3. The last law of exponent is if we have a fraction raised to a power, then each part of the fraction gets raised to that power. And I also showed you if it was to a negative power, then we can just simply flip the fraction over, and that's going to make this a positive power, and then we would distribute to each part. So a little shortcut there. But let's try this one. Suppose we had 3 to the 1/5 times 3 to the 3/5. What are we going to do? If the bases are the same, we're going to keep that common base, but what are we going to do to those exponents? We're going to multiply them, or we're going to add them? We are going to add them. So this is 4/5. Remember, most likely, the only time you really multiply exponents is if you have a parentheses kind of involved in the problem. Okay, this one a little bit harder. 7 to the 1/4 over 7 to the 1/2. So here we got like bases 7, but we're going to subtract the exponents. 1/4 minus 1/2. So that's going to be 1/4 minus 2/4. Going to change 1/2 to 2/4. So that's going to be 7 to the negative 1/4. Now, how could I write that with a positive exponent? Going to bring it down. 1 over 7 to the positive 1/4. So we're going to subtract the exponents. We need common denominators to subtract. We subtract the numerators, keep the common denominator, put 1 over it. Okay, 7.2 to the 2/3, whoops here, let me write this better, to the 2/3 raised to the 3/4. So what we're going to do here is we have a power to a power. We're going to multiply those powers. Okay, so this is 7.2, and when we multiply, we go across 6/12, and then we could reduce that 7.2 to the 1/2. And probably just leave it like that, or if you wanted a radical form, square root of 7.2. So we multiply across, if we try to reduce that, we could reduce ahead of time, but probably a little faster to do it that way. Okay, suppose we had a to the negative 1/3, b to the 2/5, raised to the 1/2. What are we going to do? We're going to multiply exponents. A to the negative 1/6, b to the positive 2/10, which we can reduce. But we're going to write these with positive exponents. Usually we want the answer with positive exponents. So we're going to bring down this a to the 1/6. And on the top, we're going to keep this b to the 1/5. Now, can we go ahead and subtract exponents? No, because these are different bases. The bases must be the same. This is a b, this is an a. So we can't do any more to the problem than that. All right. Now, sometimes we run into a little bit more complicated cases, but not that difficult. So a little trick. Well, you already know the trick. We got 6x to the 3rd. Let's rewrite this. How? X power over index. Reduce it down, 1/2. And if we want to put it back in the radical form, remember anything to the 1/2 is just a square root. Square root of x. Power 1, index 2. Pretty cool. All right. Can you get harder? Yeah, of course. 6 root of 4. Well, a couple of different ways we could handle this. Sometimes when we have a number here, we like to break it down. I like to do it a little different from the book. Well, I guess they did do it this way. But this is the 6th root of 2 squared. That's how I would think of it. Break it down. Then power over index rule, 2/6, and then reduce it, 1/3. And I don't know, I guess they want it written back in radical form. Again, 1/3 cube root. Power 1, index 3. We want to put that little index in there. Don't make the 3 so big it looks like this. Then it looks like 3 times square root of 2. You want the cube root of 2. Okay. Well, here's one, 8 a squared b4. Well, again, let's just write this as, let's take it out. A power over index, b power over index. What we're going to try to do on this one, however, is try to get them both. I guess they both want them under the same radical, but they want this a little smaller. So we could reduce this to 1/2 and this to 1/4, but let's do this. Let's reduce this to 1/4, and then let's reduce this down to 4ths also. So we'll divide both of these by 2. That way the index is the same on them. It's going to be 4 on both of these, and the power would be a to the 1, b to the 2nd. You see? And that way we can put them under a common. If we don't do that, then we got to write them as 2 separate radicals, which might, we'd have to write this as the 4th root of a and the square root of b, and that was a little bit more complicated. So this way we would put them both under the same radical. All right, let's try another one. What do we have this one? Ultimate challenges. We got the cube root of 5 times the square root of 2. And we want to simplify this. So I'm looking in my book to kind of see how they want us to do this. Well, let's get them out of radical form. This would be 5 to the 1/3. power over index. This would be 2, times 2 to the power over index, 1 half. Okay, but our bases are not the same, so we can't add the bases. So how the heck are we going to do this? Okay, so they decided, let's put them kind of like we did on this problem. Let's put them both under the same radical. Let's change this to 5 to the 2, 6, 2 to the 3, 6. Multiply both of these by 2 and then both of these by 3. Get a common denominator. Okay. Now we can put them both under the same radical. This would be the 6th root, my index, of 5 squared times 2 cubed. Like that. Now, if you wanted to go ahead and calculate that out, that would be 25 times 8. 8 times 25 is 200, 8 quarters. So this would be the 6th root of 25 times 8. What do we say? 200. That's kind of a complicated one, huh? So we change this to a radical form, a rational form, got a common denominator, therefore we got a common index, 6. Then it was 5 squared, 2 cubed. Calculated, multiplied them together, and now we got that. All right, let's see if we can try another one. A to the 1 half, B to the negative 1 half, C to the 5, 6. Now, if you wanted to change them all to common fractions right now, you could. I suppose so. Looks like they're going to keep this one with a negative exponent on top. We'll do it 2 different ways. Okay, so let's change them all to 3 6s. A to the 3 6, B to the negative 3 6, and C to the 5 6. Common denominator 6, which is our common index. This is your index. And then this would be A cubed, B negative 3, C 5. Or if you wanted to, you could write this as the cube root, the 6th root. I guess I should put it a little lower right there. The 6th root of A cubed, B will go to the bottom, and C is stay on the top. You could write it either way if you wanted to write it with positive exponents. Okay. Couple more. X to the 5 6 times Y to the 3 8 over X to the 4 9. Geez. Y to the 1/4. Well, here we do have common bases, so we could actually subtract them. So let's calculate what 5 6 minus 4 9 is going to be, because we're going to subtract those. 5 6 minus 4 9. Kind of a shortcut way of doing this is crisscross applesauce. 9 times 5, 6 times 4, 6 times 9. Multiply, multiply, multiply. Subtract 24 from 45. What would that be? 21 over 54. I think both of those are reduced by 3. 7 times 8 is 56. By 3. 3 goes into 21. 7. 3 goes into 54. 1's 18. Okay. Let's try the 3/8 and the 1/4. 3/8 minus 1/4. 12 minus 8 over 32. 4 over 32. Again, multiply, multiply, multiply. reduced by 4 1/8. Well, they don't have much in common, do they? So what they decided to do, we could write them separately. This would simply be x to the 7/18 over y, excuse me, not over, but y to the 1/8. We could leave them in that form, but they decided to get a common denominator. Well, that's kind of hard to do, you know? So let me show you another little trick. If I'm trying to find a common denominator for 8 and 18, I write the two numbers down, and I think of a number that would go into both of these evenly without any remainder. 4, 2, and 18 is 9. Now, if I multiply all these numbers together, 9 times 4 is 36 times 2. All these outside numbers will give me 72. And that's my common denominator. So I can write this as x, and I'm going to make this as 72, and 18 times 4. 18 times 4 is 72. So 18 times 4 is 72. So 24, 7 times 4 is 28. And on the y's, 8 times 9 is 72. So 8 times 9 is 72. 9 times 1 is 9. Now I can put them under the same index and write this as x to the 28th, y to the 9th. See? Then I can put them under the same radical. So I probably would do this work off to the side to get my things. Remember, crisscross applesauce, crisscross applesauce. And then this is a little trick I've learned. I found it in an old book written about 100 years ago. And I thought, this is a great idea. You can divide this by any number, just a number that would go into both of these evenly. And there aren't too many numbers. So 2, and then if you times all these together, you get your common denominator. So you multiply this one by 4 and the top by 4, this one by 9 and the bottom by 9. Okay, a couple last ones. Maybe not as difficult, let's hope. 6, let's see, this is 5x quantity to the third. Well, that would be easy. That would be just 5x quantity. Power, index, that would be just 5x to the 1/2, square root of 5x. So those won't be too hard. Okay, I don't think you're having much trouble with those. Here's one that looks a little strange. A square root, whoops there, I'm not writing this too well, of a cube root. Holy cow. So this is the square root of a cube root. Well, 2 times 3 is 6. 2 times 3 is 6. I'm going to show you this shortcut. I shouldn't do this. 2 times 3 is 6. Root of x. The book shows you a much more complicated way. You can just times these together. 2 times 3 is 6. 6 root of x. The fourth root of the fifth root of x. 4 times 5 is 20. See, easy, 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 easy. What about the square root of the square root of the square root of x? 2, 2, 2. 2 times 2 is 4. 4 times 2 is 8. It's the 8th root of x. See? So you don't have to go through a lot. And sometimes in higher math, we do end up with terrible things like this. So this is kind of a shortcut way of doing it. Just times all these together. 2 times 2 is 4, 4 times 2 is 8. Hopefully you never encounter this again in your life. All right. That's pretty much it. You will have to practice. 381. The more you do, the better you get. The better you get, the more you love math because it's not so hard then. This goes all the way to 88. And if you want to do like to 87, you know, do as many of these as you can because the better you get at them, the more you're going to enjoy them. It's just going to become a more thing. I'm just going to grab a number here, 31. I've got 7x over 8xy, yz, I mean, to the negative 3/5. Directions, rewrite with positive exponents. Simplify if necessary. Okay, how could you rewrite that? Well, look at what's our little trick? To a negative power, let's put this as a plus. Flip it over. And now it has a positive exponent. See, they don't always have to be super hard. And that one, if it doesn't ask to put it in radical form, it just said to rewrite it. It didn't say put it in radical form. You could if you wanted to. It's not that hard. It's just going to be an index. You're just going to put the 8yz and the 7x like that, and then to the third power. But if it doesn't ask for it, you don't necessarily have to do it. But it isn't hard to switch from rational form to radical form, from radical form to rational form. All right. Sorry it took so long on this video, but there's a lot to cover in a short period of time. Let's see if I can